So it is the start of special adaptive wavelength-based multi-scale image restoration. In this work, a novel, specially adaptive approach to the restoration of a noisy, blurred image, which is particularly effective, at producing sharp disconvolution while suppressing the noise in the flat region of an image. This is accomplished through a multiscale Kalman smoothing filter. Applied to a pre-filtered observed image in the discrete separable 2D wavelet domain. The pre-filtering step involves constrained least square filtering based on optimal choice for regularization parameter. This leads to a reduction in the support of the required state vectors of the multiscale restoration filter in the wavelet domain and improved in the computational efficiency of the multiscale filter. The proposed method has the benefit that the majority of the regularization or noise suppression of the restoration is accomplished by the efficient multiscale filter of wavelet detail coefficient ordered on quad tree. Not only does this lead to potential parallel implementation scheme, but it permits adaptably to the local edge information in the image. In particular, this method changes filter parameter depending on scale, local signal to noise, and orientation. Because the wavelet detail coefficient are a manifestation of the multiscale edge information in an image, this algorithm may be viewed as edge adaptive multiscale approach. Now, before going to in detail, we should study about the what does it mean. There has been a significant trend in recent research regarding the use of multiscale approaches to the image and signal processing. The increased attention to this field is largely motivated by great activity in the field of wavelets. The use of wavelets has become quite extensive in area of mathematics, mathematical physics, numerical analysis, and signal and multidimensional signal processing. As seen by this research, many processes occurring in nature may be modeled efficiently in some multiscale context. Images in particular lend themselves to this type of modeling because the presence of structures and details that may be characterized at different resolutions within the image. This is especially evident when considering the presence of an image with texture information inside it. The outline of the object may be defined by a very coarse representation of the edge, but the texture information inside the object may occur at a high frequency and could require a fine scale, high resolution representation. The edges in an image hold a great deal of the perceptual information as they define the various regions of interest in an image, and thus it is appropriate to gear image processing algorithms around these edges. In the field of an image processing, it is used to view the wavelet transform as a tool for manipulating and understanding the behavior of edges in an image. This perspective leads to algorithm encoding, reconstruction, and enhancement, which are sensitive to the perceptual importance of age to the human viewer. At the same time, interest has flourished in wavelet-based technique. A very important related theory describing optimal estimation algorithm for signals that appear in the multiscale framework has been developed. These optimal estimation ideas have led to work in non-stationary signal parametric estimation, motion estimation, texture modeling, and data fusion. The statistical theory of multiscale stochastic process can lead to an optimal way to view the behavior of wavelet scaling or detail coefficient as they evolve in scale. Utilizing multiscale stochastic estimation theory, we formalize an adaptive restoration approach here, which consistently produces perceptually pleasing results due to high quality preservation of edges in the restored images. By the way of definition, let a multiscale signal representation any collection of discrete data that appears at different scales whose support or sampling rate is dependent on scale. Here we will consider the scale and the sampling rate of data to decrease as data become coarser in this representation. The multiscale relationship between scaling coefficient of the wavelet transform is easily modeled as a weighted average process as the scale decreases. Because of this, multi-resolution estimation approaches have generally concentrated on processing the success of low-resolution approximation of an image, which are implicit in a wavelet decomposition, or on processing a quadtree decomposition of the image intensity data. It would, however, also be beneficial to apply a multiscale filter directly to the wavelet detail coefficients of an image in order to take advantage of the edge characteristics of this information at different orientation. This leads to the need for a valid description of the relationship between detail coefficients at different scales, which was investigated in different state of the art work. To simplify the discussion of the remainder, we thereafter refer to the detail coefficient of the wavelet transform as simply the wavelet coefficient and the low resolution approximation coefficient as simply scaling coefficient, as is the convention. So today we are ending for this journey here, and this will be continued in the next session. So we are ending the session over there. Thank you.